The manufacturing of a large generator at Siemens Energy Mulheim begins with the inductor, the rotating part that converts mechanical into electrical energy. Conductors are inserted and soldered using ergonomic winding stands. Ultrasound is applied to inspect the solder joints, and the winding is gradually built. Meanwhile, the stator, the stationary part, is produced in a separate area. Over 100,000 sheets are layered robotically to form the laminated stator core. After welding and rotating it horizontally, stator bars are mounted and resin impregnated under vacuum to eliminate air pockets. Back to the inductor. Precision machining shapes the shaft before a heated retaining ring is fitted. A final lathe check ensures concentricity and dimensional accuracy. Once both components are ready, the rotor is inserted into the stator, a process known as marriage. The assembled generator undergoes rigorous testing in a dedicated facility simulating real conditions. Siemens Energy's complete in-house process from winding to testing ensures durability and high performance for power plants and grid stabilization worldwide. The machining process on the Integrex begins with pre-stage cutting off to separate the raw material for initial operations. This is done at a cutting speed of 160 meters per minute with a feed rate of 0.19 millimeters/rev and a depth of cut of 0.5 millimeters, ensuring a clean and stable starting point. The machine then performs end surface turning using a multi-tool holder, operating at 430 meters per minute, a feed rate of 0.5 millimeters/rev, and a DOC of just 0.05 millimeters. This fine turning operation ensures an accurate and smooth end face of the workpiece. Following that, the machine carries out outer diameter, turning at a cutting speed of 280 meters per minute. Feed rate of 0.22 millimeters/rev, removing excess material from the outer surface. The multi-tool holder ensures consistent tool engagement and precision. Next is OD grooving, where the machine operates at 340 meters per minute, 0.36 millimeters/rev, with a DOC of 2.0 millimeters. This step cuts accurate grooves along the circumference for design or assembly requirements. Internal turning, ID turning, follows, conducted at 220 meters per minute, 0.16 millimeters/rev, removing material from the inside bore with high accuracy. Likely referring to larger internal grooves is performed at 360 meters per minute, with a feed rate of 0.26 millimeters/rev and a DOC of 2.5 millimeters, ensuring wide and precise channels inside the part. The machine then switches to burnishing, a finishing process that does not remove material, but instead polishes the surface. This is done at 360 meters per minute, 0.26 millimeters/rev, and an effective DOC of 25 millimeters, producing a smooth and hardened surface. OD turning is repeated at a high 600 meters per minute, 0.42 millimeters/rev, with a DOC of 4 millimeters, allowing for efficient bulk material removal. Another OD turning stage is shown later with cutting speed of 70 meters per minute, feed rate of 0.36 millimeters/rev, and DOC of 2.0 millimeters for finer finishing or specific geometry. Next, the cutting off process is carried out at 160 meters per minute, feed rate of 0.2 millimeters per minute, and DOC of 4 millimeters, completely severing a finished section of the part. The machine then switches to milling operations, starting with 8 mm end milling at a slower 50 meters per minute and 0.5 mm/rev, enabling precise shaping of smaller features. 25 mm end milling is next at 160 meters per minute, 0.19 mm/rev, with DOC of 0.5 mm, clearing wider paths. Later, 25 mm end milling is repeated at a much higher 900 meters per minute, 0.84 mm/rev, and DOC of 3.3 mm, indicating aggressive material removal in broader sections. Then, shoulder milling with a 50 mm cutter is carried out at 600 meters per minute, 0.56 mm/rev, and DOC of 3.75 mm, forming deep, defined steps on the component. Another shoulder milling pass is executed at 500 meters per minute, 0.45 mm/rev, and DOC of 0.5 mm, likely for refining dimensions or creating finer edges. The machine then performs M3 synchronized tapping for internal threading. This is done at 380 meters per minute, 0.45 mm/rev, and DOC of 3 mm, ensuring thread precision and synchronization between rotation and feed. Returning to cutting off, the machine executes this step at 720 meters per minute, 0.42 mm/rev, with a DOC of 2.35 mm, separating the final part with speed and stability. Another 25 mm end milling pass is made at 600 meters per minute, 0.56 mm/rev, and DOC of 2.35 mm to finalize the component surface. The sequence also includes another ID turning operation at 180 meters per minute, 0.16 mm/rev, as well as ID grooving at 200 meters per minute, 0.05 mm/rev, preparing the internal features for final tolerances or assembly. Each operation is seamlessly executed using the machine's advanced tool changers and synchronized axes, showcasing the machine's multitasking ability. From heavy turning to delicate grooving, and from high-speed milling to synchronized tapping, the machine handles the complete cycle without operator intervention, achieving high precision and cycle time efficiency. The hot metal forging process, showcased by FPM and farm brass, begins with bar sawing, where long metal bars, typically brass, aluminum, or steel, are cut into billets of uniform length. These bars are loaded automatically onto sawing machines equipped with precision blades and sensors, ensuring accurate and consistent billet dimensions. This stage is essential for maintaining volume consistency during the forging stage and minimizing material waste. Once the billets are cut, they are automatically transferred to graphitizing machines. These machines coat the billet surfaces with a thin layer of graphite-based lubricant. This coating reduces friction during forging, protects the die surfaces, and facilitates better metal flow under pressure. The graphite also acts as a thermal barrier, helping maintain billet temperature during transfer. The next critical stage is heating the billets to forging temperature. Depending on the material and application, different furnace technologies are used. For example, continuous induction furnaces and induction billet heaters are employed for brass and aluminum billets. These furnaces use electromagnetic fields to rapidly and uniformly heat the metal from within, offering precise temperature control and energy efficiency. In the case of steel, gas-fired thrust furnaces, belt conveyor furnaces, or chamber furnaces are utilized. These furnaces are designed to raise the billet temperature to over 1,000 degrees Celsius, ensuring the metal becomes malleable for deformation. Once heated, billets are automatically moved to the forging area, where they are processed by either mechanical forging presses or friction screw presses. Mechanical presses are ideal for high-volume, high-speed production, delivering consistent force with each stroke. Friction screw presses, on the other hand, are better suited for applications requiring variable force and complex shapes. These presses apply high pressure to deform the hot billet into the desired shape using precisely machined dies. The forging stations are integrated with automated loading and unloading systems. Robotic arms or mechanical manipulators handle the hot billets, positioning them correctly in the dies and removing the forged parts after each cycle. This full automation not only increases efficiency and productivity, but also enhances workplace safety by minimizing human interaction with hot materials. After forging, parts typically have excess material or flash around the edges due to die overflow. This is removed in the trimming station, where the forged components are placed in trimming presses that shear off the unwanted material. Like the forging stage, trimming is automated and synchronized with the overall line to ensure continuous operation. Following trimming, the parts undergo surface treatment processes such as deburring, sandblasting, and finishing. Deburring machines remove sharp edges and fine burrs left by the trimming operation. Sandblasting machines clean the surface of scale, oxidation, and remaining debris, resulting in a clean and uniform surface finish. These finishing processes are crucial for preparing parts for further machining, coating, or assembly. For components that require enhanced mechanical properties, heat treatment is the next step. Farm Brass provides several types of heat treatment furnaces, including continuous belt gas furnaces, chamber furnaces, and conveyor belt furnaces. These systems perform controlled heating and cooling cycles to alter the microstructure of the metal, achieving specific hardness, strength, or ductility. The heat treatment lines are fully automated, with precise temperature and time control in each zone, ensuring process repeatability and metallurgical consistency. Throughout the entire forging line, a centralized supervision and automation system manages operations. This system monitors each station in real time, controls temperatures, press forces, cycle times, and ensures product traceability. Data from each process is logged and analyzed to improve productivity, reduce defects, and allow predictive maintenance. FPM and Farm Brass deliver turnkey forging solutions that combine cutting, heating, forging, trimming, finishing, and heat treatment into a fully integrated line. Each system is tailored to the customer's material, production volume, and part geometry. In addition, the company provides lifelong after-sales support, including maintenance, remote diagnostics, spare parts, and upgrades. This advanced and fully automated approach to hot metal forging makes FPM and Farm Brass a leader in the global forging industry, serving sectors such as automotive, plumbing, energy, energy, and construction with high-quality, precision-forged components. The assembly of the M1 microcrane begins by unfolding the outrigger legs, which swing out from the sides to stabilize the crane. These legs lock securely to provide a wider base, essential for lifting heavy loads. The spring-loaded casters are then deployed to ensure balanced support. Next, the counterweight rack is slid smoothly into position at the rear of the base, enhancing stability during extended lifts. Once the base is stabilized, the vertical mast is raised and secured. The jib arm, which can be extended up to 25 feet, is then mounted and adjusted to the desired length. The galvanized aircraft cable, ranging from 100 to 160 feet, is threaded through the pulleys, connected to the 5-to-1 rated hook, and checked for proper tension. The electric winch accessory is attached for deeper rooftop or multi-story lifts up to 13 stories. After assembly, the 24 volts battery-powered hydraulic system is activated. With 90-degree steering and swivel wheels, the crane can move materials across flat surfaces and even between floors. Operators use lift points and hoist rings to secure the load before lifting. The crane's pick-and-carry capability, combined with its compact size, allows it to navigate through tight spaces like doorways, elevators, and stairwells. Operation is precise and smooth, meeting OSHA and CE safety standards. The machining and line boring of the large Namco gear case begins with precise setup on heavy-duty horizontal boring mills. Technicians use CNC equipment with digital readouts to ensure exact alignment. The gear case is then machined using a 7-axis CNC center to achieve tight tolerances. For internal bore alignment, a line boring bar is inserted and operated to precisely cut and true the bores. Milling operations follow to finish critical surfaces. Throughout the process, precision is ensured with tolerances held below 0.0005 inches. This enables the accurate machining and repair of large, custom gear cases. The manufacturing process of arb bearings begins with CNC-controlled turning to ensure precision. Heat treatment is conducted in computerized and atmosphere-controlled systems to enhance durability. The components undergo fully automatic CNC grinding and superfinishing to reduce friction, vibration, and noise. Bearings are then washed in a controlled environment for consistency. The assembly process follows a strict no-error policy, and all products are marked with unique identification codes for traceability. Quality control checks, including vibration, noise, and endurance testing, are performed at multiple stages. Finally, the bearings are securely packaged with anti-counterfeit protection and stored in a spacious facility for prompt delivery. The iter-toroidal field coil production begins by bending 750 meters of superconducting conductor into a double spiral to form a double pancake. After heat treatment at 650 degrees Celsius, the conductor is inserted into a grooved radial plate. It is then insulated with glass fiber and Kapton tape, locked with cover plates, and laser welded. 7 pancakes are joined, insulated, and vacuum impregnated with resin. After curing, dimensional checks and final assemblies are completed before transport and integration into the coil structure. To ensure a reliable water supply for southern Nevada, engineers embarked on constructing a third intake tunnel under Lake Mead. The process began by excavating a 600-foot deep access shaft using the drill blast muck method. Workers drilled deep holes into the rock, loaded them with dynamite, detonated the charges, and then removed debris using buckets lifted to the surface. Each bucket held approximately 8 cubic yards of rock. After more than a year of continuous excavation, a starter chamber and tunnel were created at the shaft's base to accommodate the tunnel boring machine. The German-built TBM, named Coil, was specially designed to withstand water pressures up to 15 atmospheres. Its 900-ton components were carefully lowered down the narrow shaft and assembled underground. TBM tunneling faced harsh conditions, including unstable geology and massive water inflows. A major setback occurred when 6,600 cubic yards of mud and gravel flooded the starter tunnel due to intersecting faults, halting progress. Engineers rerouted the tunnel to avoid the fault zone and continued excavation. The TBM operated in both open and closed modes. In favorable conditions, it used a screw conveyor to move excavated material. In high water pressure zones, it switched to slurry mode, mixing material with bentonite slurry for surface removal. Concrete ring segments were installed every 6 feet to line the tunnel. Over 14,000 segments were precisely cast off-site and placed by the TBM. Meanwhile, marine crews worked offshore to install the intake structure. A deep pit was blasted into the lakebed using remotely operated vehicles to reduce diving risks. The 1,400-ton intake structure was floated on a barge, positioned, and lowered into place using strand jacks. It was secured with 11,000 cubic yards of specially formulated concrete poured through a 350-foot tremie pipe over an 11-day continuous operation. Eventually, the TBM connected to the intake structure. Its components were dismantled and removed, and the tunnel was flooded to equalize pressure. Finally, the bulkhead separating the tunnel from the intake riser was removed, completing the connection. After nearly 7 years of excavation, engineering, and marine coordination, the third intake became operational, setting a world record for tunneling under extreme pressure and ensuring long-term water security for Las Vegas. The butt welding process for polyethylene pipes begins by cutting the pipe to the required length. The pipe sections are then positioned and clamped securely in the welding frame to ensure proper alignment. Next, the pipe ends are dressed using an end preparation tool, ensuring that they are smooth and flat. After dressing, the ends are checked to confirm they are square and aligned correctly. The pipe ends are then cleaned thoroughly with an approved cleaning solution to remove any contaminants that could affect the weld quality. A heating plate is inserted between the pipe ends to soften the surfaces. Once the appropriate heating time is achieved, the heating plate is removed carefully and the molten pipe ends are quickly pressed together under controlled pressure to form a strong, uniform joint. After welding, the joint is allowed to cool and solidify naturally. Finally, the welded pipe is stamped for future reference, including welder identification and traceability of the joint. The CIM Tech FM35T 7000 DIA machine cold forms flanges on large dish heads by rotating the head, while a forming roller presses the edge outward, gradually creating a uniform flange. The trial machining was carried out on a Skoda HORIBORERHCW using two UFK 1000 CNC spindle heads. The process began with orthogonal milling of S35C grade material using an Ingersoll D100 cutter. The depth of cut was set at 4 mm, with a spindle speed of 700 revolutions per minute and a feed rate of 1,000 mm per minute. This operation consumed 15.5 kilowatts of power. In certain milling directions and head rotations, the parameters exceeded these values. Subsequently, the machining of a spherical surface was performed using the same D100 cutter. For this stage, the depth of cut was increased to 7 mm, while the spindle speed remained at 700 revolutions per minute. The feed rate was adjusted to 800 mm per minute, and the machine power used rose to 22 kilowatts. The entire process demonstrated the machine's capability under different cutting conditions. The manufacturing process at Forgedal Group begins with forging, where metal is shaped under high pressure to refine its grain structure and eliminate porosity. Next, the material undergoes rolling to form seamless rings used in critical applications. Heat treatment then enhances the metallurgical properties of the rings. After that, components are rough or fine machined at Forgedal's specialized facilities. In the post-processing phase, welding is carried out internally to join parts and reduce customer production time. This is followed by in-house assembly of components into complete fan modules. Finally, comprehensive testing ensures all finished products meet strict quality and performance standards, completing a fully integrated and vertically streamlined manufacturing process. The production of expanded metal mesh begins by placing a steel sheet measuring 2,500 millimeters in length, 1,250 millimeters in width, and 2 millimeters in thickness onto the feed table of the APV machine. The movable control panel is used to start the process. As the sheet enters the cutting zone, a set of knives performs rapid shearing and stretching operations, transforming the solid sheet into expanded mesh. The machine completes 842 strokes. Each stroke cuts and expands the material, forming diamond-shaped openings with a web thickness of 1.5 millimeters. A mesh footage counter tracks the number of strokes. The forced winding mechanism rolls the mesh continuously as it forms. Once the sheet is fully processed, the mesh cutting mechanism activates, cleanly severing the finished mesh from the remaining sheet. The machine, with power elements designed with a twofold reserve, ensures stable operation and allows for mesh strength adjustments by modifying the bridge thickness. From a single steel sheet, 35 meters of expanded mesh is produced. The Tube QT line by DAECO processes steel tubes through quenching and tempering to improve mechanical properties. First, tubes are loaded onto the roller conveyor and pass through the induction heating system, where they are rapidly heated to the required temperature. Immediately after heating, they are transferred to the quenching station, where high-pressure water jets cool the tubes rapidly, hardening the steel. The quenched tubes then enter the tempering furnace, where controlled reheating reduces brittleness and enhances toughness. Throughout the process, automated systems ensure precise temperature and speed control. After tempering, the tubes are cooled and transferred to the straightening unit. A final inspection checks dimensional accuracy and surface quality before bundling. The entire line is designed for continuous operation, ensuring uniform heat treatment for high-performance tubular products